1 quadrillion Gauss, 2 trillion times stronger than the most powerful magnet humans have ever built. At that intensity, the magnetic field does not just pull metal. The field rips electrons from atoms, crushes spherical matter into elongated needles, and forces the empty vacuum of space to behave like a solid crystal. Only one object in the universe generates a field this extreme. And that object is a dead star. A magnetar is a stellar corpse that refuses to stay silent. When massive stars collapse under gravity, most remnants settle into quiet rotation. But a rare fraction emerge different, born with magnetic fields so intense that magnetism overpowers gravity. Magnetic energy trapped inside the crust is not a passive relic. That energy is a weapon, coiled under trillions of tons of crystalline iron, building pressure for decades until the surface shatters. A single starquake can release more energy in a fraction of a second than the sun produces across 100,000 years. In 2004, one of these flares reached the Earth from across the galaxy, 50,000 light-years away, and blinded every gamma-ray satellite in orbit. But the surface field tells only half the story. Some magnetars hide a quadrillion Gauss reservoir beneath a quiet exterior, appearing weak while the internal pressure builds toward the next eruption. Hidden giants populate the Milky Way in numbers we cannot yet count. Stars did not just form and die. Some of those stellar remnants became magnetic bombs, scattered across every galaxy, capable of erasing a world without warning. The moment of detonation is where our story begins. If you enjoy journeys that change how you see reality, hit that like button and subscribe. The proof arrived not as a visible flash, but as a digital scream inside the silicon hearts of our most advanced instruments. While humanity was distracted by the holiday celebrations of late December, the Neil Gehrels Swift Observatory encountered a signal that exceeded every design specification. The Swift hardware represents one of the most sophisticated pieces of technology ever launched into orbit, designed to detect gamma-ray bursts from the furthest reaches of the observable universe. On that afternoon in late December, the hardware encountered a wall of light that should not have existed. Physicist Kevin Hurley and the team managing the RHESSI satellite watched as the detectors saturated. Saturated is a polite word for blinded. Monitoring equipment struggled to process the surge. The incoming radiation was so dense that the electronics could no longer distinguish individual photons. Instead of a flicker, the arrival was instantaneous. When the wavefront hit the satellites at the speed of light, the astronomical community became effectively deaf and blind to the rest of the cosmos. Records from that moment reveal a flat line at the maximum possible measurement. Detectors had reached their physical limit. This impact provides a sobering look at the scale of stellar violence. Gamma radiation consists of high-energy photons that usually pass through matter with minimal interaction. However, the density of photons from SGR 1806-20 was so extreme that the atmosphere of the Earth became a giant lightning rod. In the upper layers of the ionosphere, the radiation stripped electrons from nitrogen and oxygen atoms at a rate that disrupted global radio communications. Researchers like Umran Inan at Stanford University recorded a massive disturbance in the daytime lower ionosphere. This signal was strong enough to mimic the effects of a nuclear detonation in the upper atmosphere. Under the pressure of the light, the magnetic shield of the Earth, the magnetosphere, was physically pushed inward. The geomagnetic field buckled under the strain of a star that humans could not even see with the naked eye. This star was not in our solar system. The star was not even in our local neighborhood. The source was 50,000 light-years away, hidden behind the thick dust clouds of the galactic center. To understand the energy involved, we must compare the blast to the most familiar source of power in human existence. The sun is a massive nuclear furnace that has burned for 4.6 billion years. The sun provides the energy for every plant, every storm, and every civilization in human history. If we could harvest every single photon emitted by the sun since the first humans began to walk the Earth, we would possess a massive reservoir of energy. The Magnetar SGR 1806-20 released that entire amount of energy in less than 200 milliseconds. Imagine the Earth as a small fly sitting next to a searchlight. If the searchlight turns on for a fraction of a second, the fly is obliterated. Now imagine that the searchlight is located 50 miles away. Observation of the heat from that distance reveals the impossible intensity of the source. This event was the most luminous transient occurrence ever recorded in the history of astronomy. Peak luminosity reached 10 to the power of 47 ergs per second. For a moment, this single dead star was brighter than all the other 100 billion stars in the Milky Way galaxy combined. This event created a profound mystery for the scientific community. Before 2004, neutron stars were known for their gravity and their rotation. Pulsars were the gold standard for stellar remnants, using the energy of their spin to beam radio waves across the void like cosmic lighthouses. But the math for SGR 1806-20 did not add up. The object was spinning, but the rotational energy was nowhere near sufficient to power such a cataclysmic flare. The energy had to come from somewhere else. Scientists were looking at a battery that defied the standard models of stellar evolution. This battery was not gravitational, and the battery was not nuclear. The power source was a mechanism far more exotic. The mystery was how a point of matter only 20 kilometers wide could store enough energy to blind sensors across half the galaxy. Traditional stellar puzzles lacked the necessary pieces. For decades, the official narrative suggested that dead stars slowly fade into the darkness. Yet, the reality reveals that some remnants transform into the most dangerous objects in existence. The impact on the upper atmosphere provided a laboratory for physics that no human facility could replicate. When the pulse hit the ionosphere, the burst of gamma rays created a massive surge in the density of free electrons. This sudden ionization changed the way radio waves travel through the air, causing signals that normally bounce off the sky to be absorbed or scattered. Umran Inan and his colleagues at the Stanford Very Low Frequency Group observed that the disturbance lasted for several minutes, a massive scar in the electromagnetic fabric of the sky. Radiation from the pulse was so intense that the energy deposited in the atmosphere was equivalent to the power of a 1 megaton nuclear explosion occurring every second for a full minute. This flare was not a localized event. A global synchronization occurred as the entire daytime side of the Earth felt the impact, triggered by a single point of light 50,000 light-years away. Magnetic shields protecting the planet, which usually deflect the solar wind, were temporarily compressed by the sheer pressure of the photons. This photon pressure is usually negligible in the vacuum of space, but for a fraction of a second, the light of a dead star exerted a physical force on the magnetic shield of our planet. The event served as a cosmic demonstration of electromagnetic power, revealing that the boundaries of our world are far more porous than we imagined. The signal surpassed mere arrival. The pulse commanded the entire electromagnetic environment, proving that the most powerful events in the universe are not always the largest, but the most concentrated. Our investigation must go deeper than the event itself. To understand the flare, we must understand the object that produced the flare. Humans have always been fascinated by the limits of matter. We study black holes because gravity reaches a point of no return. We study supernovae because the deaths of stars create the elements in our blood. But magnetars represent a different kind of extreme. Magnetars are the peak of electromagnetic intensity. The discovery of these objects forced us to redefine what a star can be. A magnetar is a neutron star, a remnant of a massive star that exhausted the nuclear fuel of the star and collapsed under the weight of gravity. But while most neutron stars settle into a life of steady rotation, magnetars are born with a magnetic field so intense that the field itself becomes the primary driver of the evolution of the star. The magnetic field exists as more than a secondary feature. The field defines the very existence of the star. The history of these discoveries began long before the 2004 flare. In the 1970s, astronomers began to detect strange bursts of gamma radiation arriving from random directions in the sky. These events were initially classified as gamma-ray bursts, believed to be the signatures of massive explosions in distant galaxies. But some of these sources were different. Some of these sources repeated. When the Venera 11 and 12 space probes recorded a sudden spike, followed by a series of pulsations every 8 seconds, the scientific community encountered a ghost in the machine. This 8-second rhythm was the heartbeat of a neutron star. Researchers like Evgeny Mazets identified a new class of objects, the soft gamma repeaters. A neutron star is one of the most counterintuitive structures in the cosmos. Imagine taking a star twice as massive as our Sun and crushing the entire mass into a sphere the size of a city. The density of this material is almost impossible to visualize. A single teaspoon of neutron star matter weighs as much as 900 Great Pyramids of Giza. If you drop that teaspoon on the surface of the Earth, the matter would fall through the crust like a stone through water, sinking until the matter reached the core of the planet. The gravity on the surface of a neutron star is 200 billion times stronger than the gravity of the Earth. If you stood on the surface, your body would be crushed into a layer of atoms only a few microns thick. But even this incredible gravity is not the most impressive feature of a magnetar. In these stars, the magnetic forces become stronger than the gravitational forces. The mystery of the soft gamma repeaters deepened as more data arrived. Astronomers noticed that the rotational energy of these stars was not decreasing fast enough to explain the power of the bursts. In a normal pulsar, the spin of the star provides the energy for the radiation. As the pulsar beams light, the pulsar slows down. But the soft gamma repeaters were releasing thousands of times more energy in their bursts than the stars were losing through the spin of the star. This revelation proved that a hidden reservoir of energy existed inside the star. Scientists like Robert Duncan and Christopher Thompson began to develop a radical new theory. They proposed that the energy was stored in the magnetic field itself. In their model, the magnetic field was so strong that the field could physically warp the structure of the star. This realization marked the birth of the Magnetar hypothesis. The scale of a magnetar magnetic field is difficult to articulate using human measurements. The magnetic field of the Earth is about 0.5 Gauss, enough to nudge a compass needle toward the north. A strong refrigerator magnet is about 100 Gauss. A high-resolution MRI machine in a hospital uses a field of 30,000 Gauss. The magnetic field of a magnetar can reach 1 quadrillion Gauss. This intensity represents a 1 followed by 15 zeros. To put this in perspective, a field of this strength would be lethal to a human being from a distance of 1,000 miles. The magnetic field is so strong that the field would strip the electrons from the atoms in your body, turning your biochemistry into a cloud of plasma. From the perspective of the universe, magnetism is usually a subtle force. In a magnetar, magnetism becomes a weapon of mass destruction. This shift in understanding was not immediate. In the 1980s and early 1990s, the scientific community was skeptical. Many researchers believed that the soft gamma repeaters were simply neutron stars in binary systems, stealing matter from a companion star to power the outbursts of the star. Another group of objects, known as anomalous X-ray pulsars, added to the confusion. These sources were discovered by X-ray satellites like the Einstein Observatory. Gregory and Farman found a pulsating source in the center of a supernova remnant called CTB-109. The source was strange because the source emitted X-rays at a steady rate, but the source had no companion star. The source was anomalous because the source was too bright to be powered by rotation alone. For years, these two classes of objects, the repeaters and the anomalous pulsars, were studied as separate mysteries. But how did the pieces finally come together? The Thomson and Duncan realization suggested that both AXPs and SGRs could be explained by the same mechanism, the decay of an ultra-strong magnetic field. This field decay is a violent process. As the magnetic field lines inside the star move and twist, the field lines put immense pressure on the solid crust of the neutron star. The crust of a neutron star is a crystalline lattice of iron ions, trillions of times stronger than steel. But even this material has a breaking point. When the magnetic stress becomes too great, the crust snaps. Scientists define this catastrophic failure as a starquake. A starquake releases a massive amount of energy into the magnetosphere, creating the brilliant flares that we detect from Earth. The Magnetar model provided a unified theory for the most violent events in the galaxy. The implications are profound because this model challenges our fundamental understanding of how matter behaves. In a quadrillion Gauss field, the vacuum itself becomes distorted. A phenomenon known as vacuum polarization occurs, where the magnetic pressure is so intense that the empty space around the star begins to behave like a prism. Light passing through this region is split into different polarization modes. The magnetic field is strong enough to spontaneously create pairs of matter and antimatter out of the void. We are no longer talking about simple stellar physics. We are talking about a threshold where the laws of nature transform into a state unrecognizable. The Magnetar represents more than a silent remnant. The star serves as a laboratory for the most extreme physics in the universe. The paradigm changed in that moment of theoretical synthesis. We crossed a threshold where we realized that the most powerful force in the universe was not gravity, but magnetism. The discovery of magnetars revealed a diverse family of magnetic titans that defy the laws of the laboratory. This bestiary is not a collection of identical twins, but a diverse family of monsters. To understand the magnetar, we must first understand the standard against which the magnetar is measured, the radio pulsar. A radio pulsar is a rotating neutron star that emits a beam of electromagnetic radiation. We detect these beams as pulses only when the beam points toward Earth, much like the rotating light of a coastal lighthouse. The energy of a pulsar comes from the rotation of the star. As the star slows down, the star loses energy, and the beam eventually fades. This process represents a predictable, orderly death. But then, we have the anomalous X-ray pulsars, or AXPs. These objects pulsate like radio pulsars, but the pulses arrive in the X-ray spectrum, and the objects spin much slower, usually once every 5 to 10 seconds. The anomaly that gives them their name is their brightness. AXPs are far too luminous to be powered by their slow rotation. Unlike the radio pulsars, which are powered by kinetic energy, the AXPs are powered by the slow, steady decay of an internal magnetic field. These objects emit a constant stream of X-rays, glowing with a persistent intensity that reveals the slow consumption of their magnetic reservoir. They represent the quiet phase of a magnetar, the smoldering embers of a magnetic fire. Finally, we have the soft gamma repeaters, or SGRs. These are the most violent members of the bestiary. While AXPs are steady emitters, SGRs are defined by their outbursts. They are the same objects as the AXPs, but they are in a more active state of crustal failure. An SGR is a magnetar in the middle of a starquake, releasing centuries of stored magnetic energy in a single millisecond. The distinction between these classes is not about what they are, but about what they are doing. An SGR might remain dormant for decades before suddenly erupting with a luminosity 1 billion times greater than a typical AIXP state. They are all different faces of the same magnetic titan. But what lies at the core of the investigation? We must understand how these fields are formed and how the fields eventually die. The transition from massive progenitors to silent remnants is a story of cosmic significance. We are standing at the threshold of a new understanding, looking at a star that has become a biological anomaly in the graveyard of the galaxy. This stellar remnant represents a dead heart that still beats with a magnetic pulse. By tracing the evolution of these titans, we can begin to fathom the origin of the mysterious signals arriving from deep space. Our journey through the physics of the extreme has only just begun. While the pieces of the puzzle are starting to align, The picture they form is more terrifying than we ever imagined. Sirens of the void are calling, and we have no choice but to listen. This realization that magnetism could power such massive events was a paradigm shift. In the early days of radio astronomy, the pulsar was the king of the remnants. Anthony Hewish and Jocelyn Bell Burnell discovered the first pulsar in 1967, and the world was amazed by the precision of the celestial clocks. Pulsars are reliable, pulsars are predictable. But magnetars are the chaotic cousins of the pulsars. A magnetar is what happens when the clock is overwound until the spring snaps. Humanity witnessed this catastrophic failure in 2004. The flare was the sound of a stellar crust shattering under the weight of an impossible field. The official narrative of stellar evolution is a story of balance. Gravity wants to crush the star, and nuclear fusion wants to expand the star. When the fuel runs out, gravity wins and the star collapses. For most stars, this leads to a white dwarf or a neutron star that slowly cools over billions of years. But the Magnetar model suggests that for a small fraction of stars, a third force enters the game. This force is the dynamo. During the first few seconds of a supernova, if the core of the star is spinning fast enough, the core can act like a giant electrical generator. This dynamo action amplifies the magnetic field to levels that were previously thought to be impossible. This instant marks the moment of birth for a magnetar. A star is born into a state of permanent tension, a magnetic bomb waiting for a trigger. Ultimately, the question is not whether we can understand this power. Facing the awareness of our own fragility remains the true challenge when confronted by such massive cosmic power. This magnetar serves as a reckoning for human knowledge, acting as a signal that forces exist in the darkness that we are only beginning to name. Our investigation continues, descending deeper into the electromagnetic abyss. The descent into the electromagnetic abyss reveals the strange behaviors of matter at the edge of stability. While the density of a neutron star is the foundation of the existence of the star, the internal fluid dynamics provide the mechanism for the magnetic power of the star. At the heart of the magnetar lies a core where the temperature, though reaching millions of degrees, is effectively cold compared to the extreme density. In this environment, the neutrons and protons undergo a phase transition into a superfluid and superconducting state. This superfluidity is more than a theoretical curiosity. The superfluidity is a physical reality where the material flows with zero friction and the electrical current moves without resistance. The protons in the core form a Type II superconductor, a state that allows the magnetic field lines to become trapped in trillions of microscopic tubes known as fluxoids. This pinning of the magnetic field is what allows the magnetar to maintain the quadrillion Gauss intensity of the star over thousands of years. We are looking at a quantum machine of cosmic proportions. To fathom the mechanical nature of these stars, we must look at the process of neutron degeneracy. When a massive star-exhausting nuclear fuel can no longer sustain the outward pressure of fusion, gravity wins the long struggle for dominance. The core of the star falls inward at a significant fraction of the speed of light. Under the crushing weight of the overlaying layers, electrons are physically forced into protons, creating neutrons and releasing a massive flood of neutrinos. This process, known as electron capture, transforms the stellar material into a superfluid of neutrons. The collapse only stops when the neutrons are packed so tightly that Pauli's exclusion principle prevents further compression. This creates a state of matter known as neutron degeneracy pressure. Density reached here is 1 billion tons per cubic centimeter. The material is so dense that the concept of individual atoms becomes meaningless. This star is no longer a collection of gas or plasma. The star is a single, massive atomic nucleus, 20 kilometers wide. Inside this sphere, the pressure is so extreme that the geometry of space and time is physically curved. This internal density generates a surface gravity reaching 200 billion times the force of gravity on Earth. The internal architecture of this sphere reveals a terrain of matter that challenges our definition of solid and liquid. Beneath a thin atmosphere of hydrogen and helium, lies the outer crust, which exists as a crystalline lattice of iron nuclei submerged in a sea of relativistic electrons. As we descend deeper, the pressure forces the nuclei to absorb more neutrons, creating isotopes that would be impossibly unstable on the Earth. At the base of the crust, we encounter a region of nuclear pasta. This transition zone exists between the solid lattice of the outer crust and the uniform sea of the core, where the competition between nuclear attraction and electrical repulsion creates a bizarre terrain of geometry. In this state, the nuclei are squeezed and deformed into complex shapes that resemble various forms of pasta. Scientists have identified distinct phases in this evolutionary sequence, driven by the density reaching 100 trillion grams per cubic centimeter. The process begins with the gnocchi phase, where the nuclei are compressed into spheres. As the pressure increases, these spheres merge into long parallel tubes known as the spaghetti phase. Continued compression flattens these tubes into wide, thin sheets called the lasagna phase. In some regions, the geometry inverts, creating a Swiss cheese phase, where holes of empty space are surrounded by nuclear material. These structures represent the strongest materials in the universe, 1 billion times harder to break than the highest quality steel. The sheer modulus of nuclear pasta is so high that the material can support massive mountains on the surface of the star, structures that would be flattened instantly on any other world. This pasta layer acts as the bridge between the rigid exterior and the fluid interior, a flexible but incredibly tough barrier that must withstand the twisting forces of the magnetic field. Beneath the nuclear pasta lies the core, a superfluid of neutrons mixed with a superconducting fluid of protons. Imagine the scale of this density through a new comparison. If you were to take the entire mass of Mount Everest and compress the mountain into the volume of a single marble, you would begin to grasp the density of the neutron star core. A single marble of this matter would weigh 5 billion tons. This level of concentration creates a gravitational well so deep that the light path is bent as the photons pass the surface. If you were to stand near a magnetar, you would be able to see more than half of the surface of the star at once because the gravity pulls the light from the far side around the curvature. This gravitational lensing is a visible proof of the power involved. The star is a point of maximum concentration, a place where the universe has crushed the mass of a sun into the volume of a neighborhood. This density is the prerequisite for the electromagnetic violence that follows. But does the mystery of neutron star physics end with density? Scientists remain uncertain about the exact state of matter at the very center of these objects. The Tolman-Oppenheimer-Volkoff limit provides a theoretical boundary for the mass of a neutron star. If the remnant possesses more than approximately 2.1 times the mass of the Sun, the degeneracy pressure of the neutrons fails to support the weight. The object then collapses further into a black hole. This limit creates a narrow window of existence for neutron stars and magnetars. In 1939, Robert Oppenheimer and George Volkoff worked through the general relativity equations to define this threshold. The researchers realized that the interior of a neutron star is a place of extreme uncertainty. This challenge is known as the equation of state problem. Some models suggest the core contains a soup of quarks, where the boundaries of individual neutrons dissolve, and the fundamental particles known as up and down quarks are joined by strange quarks. These strange stars will be even denser than typical neutron stars, representing a new state of matter that has existed since the first microseconds of the Big Bang. Other models propose a condensate of pions or kaons, particles that appear when the density reaches levels where the nuclear force begins to change behaviors. The data from X-ray observatories like the Neutron Star Interior Composition Explorer mission at the National Aeronautics and Space Administration continues to test these theories by measuring the radius and mass of distant remnants with unprecedented precision. We are looking at a state of matter that exists at the absolute limit of stability. This unresolved tension is the source of the magnetic potential. The existential implication of this density is a reminder of the fragility of ordinary matter. We are accustomed to a universe made of atoms, structures where the vast majority of the volume is empty space between the nucleus and the electrons. The neutron star is what happens when the universe decides to remove that empty space. This transformation represents a fundamental loss of identity for the matter involved. The atoms that once made up a massive star, with all the complex chemistry and potential for life, are ground into a uniform sea of neutrons. The neutron star is a monument to the power of gravity to erase complexity. If we cannot understand the behavior of matter at these densities, we cannot hope to understand the ultimate fate of the cosmos. Magnetars take this foundation of density and adds a layer of electromagnetic intensity that challenges the very vacuum of space. The star is not merely a dense object. The star is a catalyst for the transformation of physics. Transitions from gravity to magnetism begin with the concept of magnetic flux conservation. When the core of a massive star collapses from a radius of hundreds of thousands of kilometers down to only 10 kilometers, the magnetic field lines of the progenitor star are physically crushed together. This process is similar to taking a wide river and forcing the entire volume of water through a narrow pipe. The intensity of the flow increases by a factor of billions. In 1992, Robert Duncan and Christopher Thompson realized that this compression alone was not enough to explain the quadrillion Gauss fields of magnetars. The researchers proposed that a second process must occur, the dynamo effect. During the first few seconds of the life of a neutron star, the core is a turbulent, boiling sea of liquid neutrons and protons. If the star is born spinning with a period of only 1 or 2 milliseconds, the internal fluid motions can act as a giant electrical generator. This dynamo action amplifies the magnetic field far beyond the limits of flux conservation. The result is a field reaching 10 to the power of 15 Gauss. This dynamo process represents a moment of extreme chaos. As the star spins, the internal layers rotate at different speeds, a phenomenon known as differential rotation. This movement takes the magnetic field lines and winds them around the axis of the star-like thread being pulled onto a bobbin. This winding transforms a simple, straight magnetic field into a complex, twisted structure known as a toroidal field. While the poloidal field, the part that resembles a standard bar magnet, exits the poles and reaches into space, the toroidal field remains buried deep inside the star. This internal field is the hidden reservoir of energy that powers the magnetar. Internal toroidal fields are often 10 times stronger than the surface field, a coiled spring of electromagnetic potential that is constantly pushing against the overlying crust. The star is born into a state of permanent internal conflict, where the magnetic energy is trapped and seeking a way to escape. A magnetic field of the Sun is approximately 1 Gauss on average, though local regions near sunspots can reach several thousand Gauss. Magnetic fields of the Earth measure only 0.5 Gauss. Even the strongest magnets created by human technology, such as the superconducting magnets inside the Large Hadron Collider at the European Organization for Nuclear Research, only reach about 8 Tesla, which is 80,000 Gauss. A magnetar field is 1 trillion times stronger than the most powerful tools of humanity. This field is so intense that the field contains more energy than the gravitational binding energy of the star alone. The magnetic field is no longer a secondary characteristic of the star. The field is the dominant force governing the behavior of every particle in the vicinity. The magnetic pressure at the surface of a magnetar is 10 to the power of 18 times greater than the atmospheric pressure on the surface of the Earth. To visualize this power, consider the impact of a magnetar on human biology. If you were to approach a magnetar within a distance of 1,000 kilometers, the magnetic field does more than disrupt electronics. The field physically pulls the electrons out of the atoms in your body. The biochemistry of life depends on the sharing of electrons between molecules to form chemical bonds. In a quadrillion Gauss field, these bonds are simply obliterated. Your body would be transformed into a cloud of ionized plasma stretched into thin needles along the magnetic field lines. Even the shape of the atoms themselves would change. Spherical atoms would be crushed into long, thin cylinders. This matter stripping occurs because the magnetic forces become stronger than the electrostatic forces that hold atoms together. The magnetar is a place where the chemistry of the periodic table ceases to exist. This power creates a unique electromagnetic environment where every photon must submit to the magnetic flux. When photons of light pass through the magnetosphere, the photons encounter a region of space where the vacuum is polarized. Polarization here means that the void is no longer neutral. The void behaves like a crystal that can split light into two different parts. This is the result of quantum electrodynamics, where virtual particles in the vacuum are physically moved by the magnetic pressure. Such an effect is known as vacuum birefringence. In 2022, the Imaging X-ray Polarimetry Explorer, or IDXPE, provided the most definitive evidence for this phenomenon. By observing the Magnetar 4U0142+61, researchers detected a high degree of linear polarization in the X-ray emission. This polarization confirmed that the light was indeed being filtered by the vacuum, proving the predictions made by Duncan and Thomson decades earlier. This birefringence causes the light from the surface of the magnetar to become polarized in a specific direction, a signature that we can detect with specialized telescopes. We are seeing a region of the universe where the field is the primary architect of reality. The existential weight of this realization is that the universe possesses a level of power that can rewrite the rules of existence. We often think of the laws of physics as universal and unchanging, but the magnetar proves that these laws are context-dependent. At the peak of electromagnetic power, the very space between objects becomes a physical barrier. This realization reminds us that our experience of reality is limited to a very narrow range of conditions. We reside in a quiet corner of the cosmos where magnetism is a subtle force used for navigation and medicine. The magnetar reveals that just beyond the horizon of our understanding, a state of being exists where every particle is a slave to the magnetic flux. If the vacuum can be polarized and matter can be stripped of identity, then our definition of existence must be expanded. The magnetar exists as more than an object of study. The star serves as a signal that we are observers of a much larger, more violent reality. The mechanism that releases this power is the catastrophic failure of the stellar crust. In 1995, Christopher Thompson and Robert Duncan published a landmark paper in the Astrophysical Journal titled "The Soft Gamma Repeaters as Very Strongly Magnetized Neutron Stars." Researchers proposed that the magnetic field of a magnetar is not a static structure. The field lines are constantly twisting and moving as the magnetic energy inside the star decays. This internal movement puts an incredible amount of stress on the solid crust of the neutron star. This material is 10 billion times stronger than steel. However, the magnetic forces are even stronger. Over time, the magnetic field lines inside the star build up tension, like a spring being wound past the point of failure. This buildup of stress can last for years or decades, a silent accumulation of potential energy that has no outward sign. The physics of this failure depends on the shear modulus of the iron lattice. As the magnetic field inside the core decays, the field lines exert a Lorentz force on the ions in the crust. This force tries to drag the solid material along with the moving magnetic field. The crust resists this movement, building up elastic energy in the atomic bonds. When the stress exceeds the breaking point of the lattice, the crust physically snaps and shifts. This displacement can be as small as a few millimeters, but at the density of a neutron star, a millimeter shift is a cataclysmic event. The sudden movement releases a massive wave of energy into the magnetosphere of the star. This process is a starquake. The energy released is trillions of times greater than the energy of the largest earthquakes on the Earth. A starquake on a magnetar releases more energy in a fraction of a second than the total seismic energy released by the Earth over the course of millions of years. Imagine the starquake through the examination of the mechanical clock analogy. Picture a clock where the mainspring is made of a material so strong that the spring can store the energy of 1,000 nuclear bombs. As the clock runs, the spring slowly unwinds, but occasionally the gears jam. The tension builds and builds, the metal groaning under the strain. Eventually, the metal cannot hold any longer. The gears shatter, and the spring releases all the stored energy in a single violent burst. The clock does more than stop, the clock explodes. This is the life of a magnetar. The magnetic field is the spring, and the stellar crust is the gear system that tries to contain the energy. A starquake is the moment of failure, the moment when the container can no longer hold the contents. This analogy helps us visualize the relationship between the internal field decay and the external flares. The star is a magnetic bomb that is constantly being armed by the evolution of the star. The anomaly of this mechanism is the relationship between magnetic energy and rotational energy. In a standard pulsar, the rotational energy drives the emission. As the pulsar spins down, the pulsar loses kinetic energy, which is converted into radio waves and light. However, magnetars release far more energy in their flares than the stars lose through rotation. This was the smoking gun that proved a different power source was at work. The energy must come from the magnetic field alone. This field decay is a form of entropy on a cosmic scale. As the magnetic field lines untwist and dissipate, the energy is converted into heat and radiation. This process is facilitated by the release of neutrinos, which carry away the thermal energy and allow the magnetic field to continue the descent of the field into a lower energy state. This neutrino cooling is the silent companion to the magnetic decay. During the first century of the life of a magnetar, the temperature of the core remains above 1 billion degrees. At these temperatures, the star is a prolific source of neutrinos. This cooling determines how the magnetic field evolves, because the electrical conductivity of the superfluid neutrons depends on the temperature. If the star cools too slowly, the magnetic field could remain active for longer periods. If the cooling is rapid, the magnetic reservoir might be exhausted within a few thousand years. This link between thermal physics and electromagnetism is what defines the narrow window of visibility for these objects. We are seeing them during a brief, violent youth that will eventually fade into a cold and silent middle age. Ultimately, the starquake is the peak of power in the cosmos. Can the human mind truly grasp the realization that a city-sized object can outshine 100 billion stars? The starquake serves as a reminder that the universe does not operate on a human scale. We are observers of a reality that is far more intense and unpredictable than our daily existence suggests. The magnetar serves as a reckoning for our knowledge of matter and energy, acting as a signal that the most powerful events in the universe are often hidden in the smallest points of matter. As our examination continues, we must look at the anomalies that challenge even this successful model. We must examine the low-field magnetars and the mysterious radio pulses that suggest our understanding of the bestiary is still incomplete. The electromagnetic abyss is deeper than we imagine, and the starquakes are only the beginning of the story. The entire paradigm changed in the moment we realized that the stars can scream. Everything changed in that moment in 2010, when the astronomical community encountered a contradiction that threatened the foundational logic of stellar evolution. Nanda Ria, an astrophysicist then at the University of Amsterdam, led a team observing a source designated as SGR 0418 plus 5729. The object had been identified as a soft gamma repeater, a class of stars synonymous with extreme magnetic power. However, when Rhea and her colleagues measured the spin-down rate of the star to calculate the strength of the surface magnetic field, the results were impossible. The surface dipole field was measured at only 6 trillion Gauss. While 6 trillion Gauss sounds massive compared to the half-Gauss field of the Earth, this value is 100 times weaker than any other known magnetar. According to the standard model, a field this weak should not have the energy to fracture the crust or produce the signature flares of the magnetar class. The discovery was a theoretical crisis. The star was behaving like a monster while appearing as a ghost. This anomaly suggested that the outward appearance of a star might be a deceptive mask. The team had to check the data 3 times to ensure the sensors were not malfunctioning, but the numbers remained steady. A star with the field of a common pulsar was screaming with the voice of a magnetar. The mechanics of this deception involve a hidden reservoir of energy. We typically measure the poloidal field, the external magnetic flux that reveals the age and power of the object to our telescopes. But the work of Nanda Ria and subsequent theoretical models proposed that deep beneath the iron crust, a toroidal field exists. This internal field is likely reaching 1 quadrillion Gauss. The magnetic field lines inside the core are under such extreme tension that the flux lines occasionally push through the surface in small, concentrated loops. These loops are 100 times stronger than the global field, creating localized regions of electromagnetic violence on an otherwise quiet star. This realization forced a re-evaluation of the entire neutron star population. This discovery means that thousands of stars we currently classify as dormant pulsars might actually be low-field magnetars, waiting for the internal tension to reach a breaking point. We are surrounded by hidden potential. The magnetic pressure inside such a star is so immense that the internal fluid is physically distorted, a state of permanent structural stress that the exterior of the star successfully hides from the prying eyes of humanity. To confirm this, Rea utilized a deep observation with the XMMM X-ray Observatory in 2009. The team identified a specific absorption feature in the spectrum that varied as the star rotated. This feature was the signature of a proton-cyclotron line, a clear signal that the local magnetic field near the surface was actually 1,000 trillion Gauss, even if the global field appeared weak. The data proved that the monster was not gone, the monster was simply submerged. A proton-cyclotron line occurs when protons in the magnetosphere of the star are forced into circular orbits by the intense magnetic field. The energy required for this movement is tied directly to the field strength, creating an absorption notch in the X-ray spectrum at a very specific frequency. By measuring where this notch appeared, Nanda Rea was able to weigh the local magnetic field. The results confirmed that while the global dipole field was weak, the surface was peppered with magnetic loops of terrifying intensity. These loops are formed by the twisted toroidal field lines that are being forced out through the crust like the loops of a solar flare. This discovery changed the way we look at the neutron star population, suggesting that the active life of a magnetar might be much longer than we suspected. The star does not lose the magnetic energy. The star merely hides the energy where we cannot easily see the reservoir. This hidden reservoir can survive for tens of thousands of years, a coiled spring of electromagnetic energy that remains dangerous long after the external signature has faded. We are essentially looking at a celestial body that has mastered the art of the hidden threat. Beyond the initial detection, the team had to account for the lack of obvious radio or X-ray thermal emission that usually accompanies such powerful objects. SGR 0418 plus 5729 remained stubbornly quiet between the bursts of the star. This behavior suggests that the magnetic energy is trapped so efficiently that only a catastrophic failure of the crust can release the energy. Scientists now believe that these low-field magnetars might be more common than their high-field cousins, representing the silent majority of the magnetar population. They are the sleepers of the galaxy, stars that have aged enough for their external fields to decay, but whose internal fires still burn with quadrillion Gauss intensity. This realization adds a layer of unpredictability to our understanding of the Milky Way. We are mapping a minefield where the mines are invisible until they explode. Imagine the surface of a deep and silent ocean. To an observer on a ship, the water looks calm, the waves are small, and the horizon is peaceful. This is the poloidal field we measure from a distance. Beyond this tranquil surface, miles below the hull, a massive tectonic rift is opening. Magma is boiling, pressure is building, and the very foundation of the seabed is ready to explode. Yet, the observer on the ship sees no sign of the danger until the moment the tsunami hits. The magnetar represents the tectonic rift, and the calm ocean represents the weak external field. The energy is not in the waves we can see. The energy is in the pressure we cannot. This star proves that the map is not the territory. The universe does not always display the full extent of the power of the star on the surface. We are looking at a celestial body that has mastered the art of the hidden threat. If you were to bring a compass near such a star, the needle would not just point north, the needle would be physically vaporized by the localized loops of magnetism that the global field fails to report. The star is a master of the electromagnetic lie. The mystery deepened when researchers looked at the age of these low-field objects. If a magnetar is born with a quadrillion Gauss field, the field should decay over thousands of years as the star releases energy through flares and heat. Some researchers argued that SGR 0418 plus 5729 is simply an old magnetar, a remnant that has exhausted the external field but still retains a core of high intensity. But this creates a problem of timing. If the field decays that slowly, then the number of active magnetars in the Milky Way should be much higher than we observe. Others propose that these objects are born this way, with a mismatch between the internal and external power from the very first millisecond of existence. This conflict of models is more than a technical debate. The conflict is a struggle to understand the life cycle of the most extreme matter in existence. The data from Rhea suggests that our bestiary of neutron stars is not a collection of distinct species, but a single, complex lineage that changes appearance as the internal clock winds down. The star might start as a bright and violent youth, only to hide the remaining power in the core as the external field fades into the background noise of the galaxy. This hidden reservoir could last for tens of thousands of years, far longer than the active life of a standard magnetar. This revelation carries a profound existential weight, forcing us to acknowledge that the cosmos is populated by these hidden sleepers. We exist in a cosmos where the most dangerous objects can hide in plain sight by appearing weak. This realization reflects a fundamental truth about the limits of human observation. We judge the power of the universe by what we can measure, but we can only measure the light and the fields that reach our senses. The low-field magnetar is a reminder that the silence of the galaxy is not necessarily a sign of peace. The silence might be a sign of a build-up. Every point of light in the sky is a potential mask, and the true nature of reality is often buried beneath a crust of iron and shadow. We are observers of the surface, trying to fathom the depth. The implications are profound, because this discovery suggests that the inventory of cosmic threats is far larger than we suspected. The galaxy is not a well-mapped territory. The galaxy is a dark room full of objects that we only see when they decide to scream. But the complexity increases here as we turn our attention from the invisible fields to the mysterious signals that these stars broadcast into the void. For decades, the consensus was that magnetars were radio silent. Pulsars used rotation to power their radio beams, while magnetars used magnetic decay to power X-rays. These two worlds were thought to be separate, divided by an evolutionary wall that no star could cross. Everything changed in that moment in 2006 when Fernando Camilo and his colleagues at the Parkes Observatory in Australia turned their radio telescope toward a known magnetar called XTE J1810-197. The star had recently undergone a massive X-ray outburst, but no one expected to hear a radio signal. To the shock of the team, the magnetar was pulsing with intense broadband radio waves. This was the first time a magnetar had ever been detected at radio frequencies. The signal was not the steady, predictable ticking of a pulsar. Instead of a rhythmic heartbeat, the signal was erratic and violent, changing the structure of the signal every few minutes. The data meant the boundary between the two classes of neutron stars had been shattered. Fernando Camilo had been monitoring the source for months, searching for any sign of radioactivity that might follow the X-ray flare. When the signal finally arrived, the intensity was staggering. The radio pulses were not just present, the pulses were among the brightest radio sources in the sky. This discovery forced the community to rethink the relationship between magnetism and radio emission. Utilizing the 64-meter dish at Parkes, the team tracked the star as the pulses evolved. They found that the pulses were characterized by a flat radio spectrum, meaning the pulses emitted energy with nearly equal intensity across a vast range of frequencies. This behavior is fundamentally different from traditional pulsars, which usually show a steep decline in brightness as the frequency increases. The Magnetar was not just a dense star. The Magnetar was a cosmic broadcaster that was rewriting the rules of radio astronomy. This radio emission provides a potential link to the greatest mystery in modern astronomy, the fast radio bursts. These distant radio flashes arrive from billions of light years away, representing a universal anomaly that had remained unsolved for years. But the discovery of radio pulses from a local magnetar suggests that these cosmic giants might be the engines behind the flashes. If a local magnetar can produce radio waves that outshine the rotation of the star, imagine what a magnetar in a distant galaxy could do during a giant flare. The signals Camilo detected were the first breadcrumbs on a trail that leads to the edge of the observable universe. We are looking at a universal phenomenon, a way for the universe to communicate across distances that defy human imagination. The mechanics of this radio emission reveal a fundamental difference in how magnetars interact with the vacuum. Traditional radio pulsars operate as kinetic engines, drawing their luminosity from the steady loss of rotational energy. Electrons are accelerated along the magnetic field lines, creating a coherent beam that sweeps across the Earth like a lighthouse. But the radio emission from XTEJ 1810-197 was different. The radial pulses were far more luminous than the rotational energy of the star could account for. This meant the radio waves, like the X-rays, were being powered by the decay of the magnetic field. The magnetic field lines were twisting in the magnetosphere, creating regions of intense electrical current that accelerated particles to relativistic speeds. These particles then released radio waves through a process that remains a subject of intense study, the energy being pumped into the environment by magnetic reconnection events, rather than the smooth acceleration of a rotating dipole. Imagine a broken lighthouse on a rocky coast. A standard pulsar is the working lighthouse, spinning at a perfect rate, with the radio beam cutting through the fog with mathematical precision. You can set your watch by the pulses. But a radio-loud magnetar is a lighthouse where the lamp is malfunctioning and the gears are grinding. The beam flickers, the beam changes color. Sometimes the beam disappears for hours, only to return with a blinding intensity that exceeds the design of the lamp. The power is not coming from the motor that spins the light. The power is coming from a short circuit in the wiring. The radio emission is the sound of the magnetic field failing. This analogy helps us understand why the radio pulses are so transient. The signal only appears when the magnetosphere is twisted by a recent crustal shift. When the field untwists and the energy is dissipated, the radio signal fades away, leaving the star in silence once again. The magnetar is a radio station that only broadcasts when the building is on fire. The anomaly of the radio-silent magnetar remains one of the most persistent puzzles in high-energy astrophysics. If one magnetar can produce radio waves, why are most of them silent? Fernando Camilo and other researchers have spent years searching the galaxy for more examples, but they have only found a handful. This scarcity suggests that the conditions required for radio emission are incredibly specific. The star must have the right magnetic geometry, the right rotation rate, and perhaps most importantly, the right amount of recent crustal activity. Some models propose that the radio emission is suppressed in most magnetars because the dense plasma of the magnetosphere traps the radio waves before the waves can escape. Only during the aftermath of a major flare is the magnetosphere cleared enough for the radio beam to pierce the veil. This creates a selection bias in our observations. We only see the radio-loud magnetars when they are in a state of extreme agitation. This realization challenges our understanding of the neutron star population by suggesting that the radio-silent majority might just be waiting for their moment of broadcast, especially if no disk exists. Such a radio signal is a voice from the abyss, a reminder that the most extreme objects in the universe have more ways to communicate than we ever imagined. These implications are profound because if magnetars can produce radio pulses, then they might be responsible for other mysterious signals from the deep reaches of space. This connection between these local monsters and the distant flashes of energy known as fast radio bursts is the threshold of a new understanding of the universe. We crossed a threshold of understanding when we realized that these objects do not just defy our categories of emission, the objects defy our categories of time. This temporal distortion is most visible in a supernova remnant designated as RCW-103. At the center of this expanding shell of gas sits an object known as 1E161348-5055. When Andrea De Luca and his colleagues examined this source in 2006, they expected to find a young, fast-spinning neutron star, typical of a remnant only 2,000 years old. But the data from the X-ray telescopes revealed a rotation period of 6.7 hours. For a neutron star, a 6.7-hour day is not just slow, the period is physically impossible according to standard evolution. A neutron star should be born spinning dozens of times per second. To slow down to a 6.7-hour period in only 2,000 years requires a braking force that exceeds anything we have ever measured. The star was moving through time at the speed of a glacier while residing in a cradle of fire. The mechanics of this extreme braking involve a process that sounds like science fiction, the fallback disk. After the initial supernova explosion, not all of the stellar material is ejected into space. Some of the gas falls back toward the newly formed neutron star, creating a dense disk of material that surrounds the object. This disk interacts with the intense magnetic field of the magnetar, creating a massive amount of friction. As the magnetic field lines sweep through the disk, the lines act like a set of brakes, dragging against the material and pulling on the rotation of the star. In the case of the object in RCW-103, this interaction was so efficient that the star was slowed from a millisecond period to a 6.7-hour period in a geological blink of an eye. This requires a magnetic field of incredible strength, likely in the quadrillion Gauss range, to provide the necessary torque. The star is not just spinning, the star is fighting through a sea of stellar debris. But what if no disk exists? This question has led to one of the most intense debates in stellar physics. Some researchers argue that the braking could be caused by an even more extreme magnetic mechanism, known as magnetic dipole radiation, combined with a high braking index. If the magnetar is born with a magnetic field that is not aligned with the axis of rotation, the magnetar will emit a massive amount of electromagnetic energy. This emission provides a torque that could theoretically slow the star down without the need for a fallback disk. However, this model requires a magnetic field that is at the absolute limit of what physics allows. Andrea De Luca and others continue to monitor the source for any changes in the rotation rate, but the star remains stubbornly slow. If the fallback disk exists, we should see evidence of the material in the infrared or submillimeter spectrum. So far, the searches have been inconclusive. We are seeing a result that we can describe, but we cannot yet fully explain. The environment of RCW-103 adds another layer of complexity. The supernova remnant is a chaotic web of glowing filaments and heated dust, a shell of matter that is still expanding outward into the interstellar medium. Heated to millions of degrees, the gas emits a soft glow in the X-ray spectrum that surrounds the central source like a shroud. Inside this cradle of fire, the magnetar sits in isolation, where the slow rotation remains a silent testimony to the violence that occurred 2 millennia ago. The cooling of the gas and the decay of the field are the only clocks that remain. This isolated environment provides a unique laboratory for studying the end state of magnetar evolution. Imagine a professional figure skater on a sheet of ice. The skater begins to spin faster and faster until the skater is a blur of motion. This is the birth of a neutron star. Now imagine that the ice suddenly turns into thick, cold maple syrup. The skater tries to maintain the spin, but the syrup grabs at the skates and the clothing. The rotation slows down instantly. Within seconds, the skater is barely moving, struggling to complete a single turn. The syrup represents the fallback disk, and the skater represents the magnetar. The friction is so high that the kinetic energy of the rotation is converted into heat and dissipated into the environment. This analogy helps us understand the sheer magnitude of the breaking index involved. We are looking at an object that has been robbed of all momentum by the very explosion that created the star. Evidence of this cosmic struggle is written into the very rotation of the star. That 6.7-hour day represents the signature of a braking force that should not exist. This existential implication of slow rotation is the realization that the universe can erase the history of a star in an instant. The kinetic energy that a star accumulates over millions of years of life can be stripped away in a few centuries. This transformation is a form of cosmic amnesia. The remnant in RCW 100 no longer remembers the fast rotation of the youth of the star. The star has been forced into a state of premature old age by the violence of the local environment. This reminds us that the evolution of the cosmos is not a smooth and predictable journey. The journey is a series of catastrophic events that can rewrite the properties of matter and time. The implications are profound, because if a magnetar can be slowed to a 6.7-hour period, then the range of possible behaviors for these stars is far wider than our early theories predicted. We are looking at a universe where the extreme is the norm and the impossible is just a matter of time. Our search for answers continues as we look deeper into the void, discovering that these local anomalies are the key to understanding the most powerful signals in the history of astronomy. Those pieces of the puzzle are starting to fit, but the picture they form is more terrifying than we imagine. The next chapter of the story takes us beyond our galaxy to the flashes of light that defy the laws of distance. The connection between the magnetar and the fast radio burst is about to be revealed. The pursuit of the cosmic boundary begins with a recognition of the silence between the stars. For decades, radio astronomers viewed the night sky as a predictable sequence of steady hums and rhythmic pulses. Pulsars ticked like clocks, and galaxies glowed with the soft, diffuse heat of ancient gas. But in 2007, a graduate student named David Narkovich and the advisor of the student, Duncan Lorimer, were examining archival data from the Parkes Observatory in Australia. They were not looking for a revolution. They were looking for pulsars in the small Magellanic Cloud. Instead, they found a signal that defied every known category of celestial emission. This single flash of radio waves lasted for less than 5 milliseconds, yet the energy contained within that brief moment was staggering. The signal was 500 times brighter than the brightest pulsar in the Milky Way. When the team calculated the distance to the source, the results were impossible. The signal had traveled for more than 1 billion light-years. This event, now known as the Lorimer burst, was the first evidence of a phenomenon called a fast radio burst. The universe was screaming in a language we did not yet understand. Everything changed in that moment because the scale of the cosmos suddenly felt more violent and more connected than we had ever dared to imagine. The mechanics of this detection involve a property of space known as dispersion. As a radio signal travels through the vacuum, the signal encounters free electrons that populate the intergalactic medium. These electrons act like a translucent fog. Higher frequency radio waves move through this fog slightly faster than lower frequency waves. This means that a signal that begins as a sharp, simultaneous flash will arrive at Earth as a smeared-out whistle, with the high notes hitting the telescope first and the low notes arriving a fraction of a second later. This time delay is called the dispersion measure. By calculating the amount of smearing, David Narkovich and Duncan Lorimer could determine exactly how much matter the signal had passed through on the journey of the signal. The dispersion they measured was massive. This signal had crossed such a vast expanse of empty space that the origin had to be far beyond the boundaries of our own galaxy. The luminosity required for a signal to be visible from 1 billion light-years away is almost incomprehensible. This flash of energy was equivalent to the total power output of the sun over the course of 80 years, all compressed into a window of time shorter than the blink of a human eye. The discovery of the Lorimer burst proved that the universe possesses a mechanism for broadcasting energy across cosmological distances with terrifying efficiency. Imagine a vast and pitch-black football stadium. You are standing in the center of the field and you've been told that the arena is empty. For hours, you hear nothing but the faint rustle of the wind. Then, for a single millisecond, a flashbulb ignites at the very top of the highest bleacher. The light is so intense that the flash blinds you. Before you can even turn your head to see where the light came from, the stadium is dark again. The fact that you could see the flash from the center of the field means the source was incredibly powerful, yet the brevity of the event means the source must be very small. A star the size of the sun cannot change the level of brightness in a millisecond. The laws of light speed prevent such a rapid transformation. Only an object the size of a city, like a neutron star, can release energy so quickly. This analogy helps us understand why the astronomical community was so unsettled by the discovery. We found a strobe light at the edge of the cosmos, and we had no idea who was holding the camera. The mystery of the origin of these signals sparked a decade of intense debate. Some researchers suggested that the bursts were caused by the collision of two black holes or the final collapse of a massive star. These are cataclysmic events that can only happen once. But in 2012, a team led by Victoria Kaspi and Jason Hessels discovered a source called FRB 121102 that began to repeat. The same point in the sky was flashing again and again. The discovery eliminated the possibility of a one-time explosion. The engine behind the signal had to be something that could survive the release of such immense power. This realization pointed the finger directly at magnetars. We knew that magnetars could produce giant flares of gamma radiation, but we had never seen them produce a radio signal strong enough to be seen from another galaxy. The community was divided. Some argued that the repeating bursts were evidence of advanced alien civilizations using massive beams of energy to power interstellar sails. Others argued that the signals were the natural byproduct of a young magnetar residing in a dense and chaotic environment. The lack of a local example made the debate impossible to resolve. We were looking at a universal anomaly without a local anchor. The question was no longer about the nature of the signals, but rather the mechanism behind such extreme luminosity. The existence of these distant signals carries a heavy existential weight. We are observing the universe not as a collection of static objects, but as a web of energetic events that link the most distant galaxies to our own sensors. Every fast radio burst is a ghost from the past, a signal that has been traveling for billions of years before finally reaching the metal dishes of our telescopes. This reminds us of the staggering scale of the time and space that separates us from the rest of existence. If these signals are indeed produced by magnetars, then the universe is populated by billions of these magnetic monsters, each acting as a signal in the dark. We are part of a cosmic conversation where the speakers are dead stars and the words are flashes of pure energy. This realization forces us to confront our own fragility. A single burst of this magnitude, if such a burst occurred within our own solar system, would be a terminal event for our civilization. We are surviving in the quiet gaps between the screams of the cosmos. The signal is a reminder that the universe does not just exist. The universe communicates through violence. The implications are profound because we finally found a local anchor for this mystery in 2020. Everything changed in that moment on April 28, 2020, when a magnetar inside our own galaxy decided to speak. The object was SGR 1935 plus 2154, a well-known member of the Magnetar bestiary, located about 30,000 light-years away. For weeks, the star had been in a state of extreme agitation, releasing dozens of X-ray bursts. Then, at exactly 1438 Universal Time, two massive radio telescopes in North America detected something impossible. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, and a project called STARE-2, recorded a radio burst that was millions of times brighter than any radio signal ever seen from a star in the Milky Way. This burst was the smoking gun. For the first time, scientists had captured a fast radio burst from a source they could already identify. The signal was so powerful that a simple radio receiver made from a cell phone could have detected the pulse if the receiver had been tuned to the correct frequency. such a monster was no longer a distant mystery. Instead, this monster was in our own backyard. The mechanics of this detection involved a simultaneous observation across the electromagnetic spectrum. As the radio pulse hit the antennas in Canada and the United States, a fleet of X-ray satellites, including the Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope, captured a simultaneous burst of high-energy radiation. The detection was the moment of verification. The radial burst and the X-ray burst arrived at the same time, proving they originated from the same physical event on the surface of the Magnetar. This pairing of signals allowed researchers to calculate the efficiency of the engine. The star was converting a fraction of the magnetic energy of the star into radio waves with a level of coherence that shattered our previous models. This coherence is the key to the brightness. In a normal star, atoms release light randomly, like a crowd of people talking at once. But in a coherent burst, every electron moves in perfect unison, like a stadium of people shouting the same word at the same time. The resulting signal is far louder than any other source and represents a different category of power. This event proved that magnetars possess the capability to produce the signals we have been seeing from the edge of the universe. Imagine you have a collection of thousands of antique keys. You have been searching for the locks that these keys open for your entire life, but you have never found a match. You travel across the world, looking at ancient doors and forgotten chests, but nothing fits. Then, one day, you walk into your own kitchen and notice a small drawer that you have never opened. You take the key from your pocket, the one you found in a distant ruin, and you slide the key into the lock. The key fits perfectly. The drawer slides open. This is what the detection of SGR 1935 plus 2154 felt like for the astronomical community. We had the key of the fast radio burst, and we finally found the lock on a local Magnetar. The match was undeniable. The match meant that we did not need to invent new physics or invoke alien civilizations to explain the signals from deep space. The answer was already in our catalog of dead stars. The local monster was the universal source. This analogy helps us understand the sense of relief and awe that followed the discovery. We finally understood the language of the screams. The controversy surrounding this discovery remains an active field of study. While SGR 1935 plus 2154 proved that magnetars can produce these bursts, the detection did not prove that all fast radio bursts come from magnetars. The burst from our galaxy was still thousands of times weaker than the most powerful bursts we see from other galaxies. This discrepancy suggests that there may be a hierarchy of power. Perhaps the repeating bursts come from young, hyperactive magnetars, while the one-time events come from different sources entirely, such as the collision of neutron stars or the collapse of a pulsar. Some researchers argue that the environment surrounding the magnetar plays a critical role. A magnetar residing in a young supernova remnant or a dense star-forming region might be able to amplify the signals of the star through interactions with the surrounding plasma. This debate highlights the complexity of the cosmic environment. We have found the engine, but we are still mapping the exhaust system. The data from the 2020 event is a foundation, but the foundation is not the entire building. The realization that magnetars are the primary suspects for these universal signals carries a staggering weight. We are looking at a population of stars that acts as a cosmic broadcasting network. If every galaxy contains thousands of magnetars, and each magnetar can release these bursts over the lifetime of the object, then the universe is literally shimmering with radio light that we are only just beginning to detect. This transforms our view of the cosmos from a cold and silent void into a busy and energetic arena. We are the observers of a massive automated telegraph system. The realization changes the relationship between humanity and the distant universe. The signals are no longer just noise. The signals are data points that can tell us about the history of the matter between the galaxies. We are using the light of dead stars to map the invisible architecture of the cosmos. The flashes represent a form of universal communication that does not require a sender or a receiver. The signal is the message, and the message is that the universe vibrates with electromagnetic tension, a tension that precedes the final silence. The implications are profound, because this discovery suggests that magnetars are the universal broadcasters of the cosmos. If magnetars are responsible for the majority of fast radio bursts, then we can use these signals to perform a census of the universe. As each burst travels through billions of light-years of space, the signal carries a record of every electron and every cloud of gas encountered on the path. This allows astronomers to weigh the universe. We can measure the total amount of normal matter, the baryons that exists in the vast voids between the galaxies. This matter is otherwise invisible to our telescopes because the gas does not emit light from the atoms of the gas. But the dispersion of the fast radio burst reveals the presence of this matter with mathematical precision. The sonar effect is the ultimate utility of the extreme. The most violent objects in existence are providing the tools to solve the most fundamental mysteries of cosmology. We are observing the peak of power and using that radiation to illuminate the invisible architecture of the void. The mechanics of this universal broadcast involve a process known as curvature radiation from charged bunches. Within the magnetosphere of the magnetar, the magnetic field lines are so curved that relativistic particles are forced to move along paths of extreme tight radius. As these particles accelerate, they release radiation. In a magnetar, the magnetic energy is so dense that particles do not move individually. They form into massive bunches of millions of electrons and positrons. These bunches move in perfect coordination, creating a coherent beam of radio waves that is directed along the magnetic axis of the star. The magnetar serves as the cosmic telegraph. The energy for this broadcast comes from the decay of the magnetic field, which acts as a battery that can dump quadrillion Gauss of energy into the environment in a few milliseconds. This process is so efficient that the beam can outshine the entire radio output of the entire system of a galaxy. The rapid expenditure of energy is not a sustainable state. The magnetar is burning through the life force of the star to produce these signals, a rapid and violent expenditure of energy that eventually leads to the silence of the star. Imagine a massive network of lighthouses stretching across the entire surface of the Earth. Each lighthouse is positioned on a different continent, and each one is separated by thousands of miles of ocean. For most of the time, the lighthouses are dark, but every few hours, one of the lights flashes with a beam so bright that the beam is visible from the moon. No pattern governs which lighthouse flashes next. Sometimes a single light flashes 10 times in a row, and then stays dark for a century. This network represents the global population of magnetars. The flashes are the fast radio bursts. To an observer on the moon, the Earth would appear to be covered in a shimmering, irregular grid of light. The signals reveal how the universe appears to our radio telescopes. We are seeing a web of signals that reveals the locations of the most extreme matter in the cosmos. The signals are the heartbeat of a universe that is constantly recycling all remaining energy through the most violent channels possible. This analogy helps us understand the sheer numbers involved. Hundreds of millions of magnetars likely populate the observable universe, each one contributing to this shimmering cosmic pattern of signals. By studying the bursts from SGR 1935 plus 2154, we are learning the physics of objects that reside on the far side of the observable universe. The observation is a form of intellectual travel. We do not need to visit a distant galaxy to understand the contents of the distant system. We only need to listen to the signals the magnetars of the host are sending us. This realization enhances our sense of cosmic citizenship. They are not just rare accidents, they are a key stage in the life cycle of matter. Every galaxy produces them, and every galaxy is shaped by their presence. We are looking at a universal constant of extreme physics. The existence of these signals also provides a way to test the fundamental constants of physics. Because the signals travel over such vast distances and through such extreme magnetic fields, they are sensitive to any variation in the speed of light or the strength of gravity. Scientists are using fast radio bursts to search for evidence of extra dimensions or changes in the laws of physics over cosmic time. If the signal from a magnetar a billion light-years away arrives exactly as our models predict, the signal is the ultimate verification of our understanding of reality. The magnetar is not just a star. The magnetar is a laboratory that spans the entire universe. We are using the most extreme conditions imaginable to confirm that the foundations of our world are stable. The stability provides a sense of intellectual satisfaction that balances the existential dread of the power of the star. But as we look closer at these cosmic broadcasters, we realize that their voices are not eternal. The energy that powers the broadcast is a finite resource. Each burst, each flare, and each pulse is a withdrawal from the magnetic bank account of the star. The quadrillion Gauss field is a coiled spring that must eventually unwind. This brings us to a sobering realization. The most powerful objects in the universe are also the most fleeting. A magnetar only stays active for about 10,000 years, a mere heartbeat in the life of a galaxy. After that, the field decays, the flares stop, and the star becomes a silent, cold remnant of iron and ash. We are witnessing a brief and violent moment in the life of matter. The screams we hear from deep space are the sounds of stars dying in a final, brilliant display of electromagnetic defiance. These signals are beautiful, but the signals are also a warning. The power has a price, and the price is the eventual descent into the void. This brings us to the final threshold of our investigation, the moment when the lights go out and the monster becomes a ghost. Our descent into the physics of the absolute concludes with the realization of what remains when the magnetic fire is gone. That path leads to the silent remnants that populate the dark corners of the Milky Way, the final destination for every titan of the void. The revelation that fast radio bursts originate from these magnetic monsters completes our map of the active universe. But as we solve the mystery of their youth, we must confront the reality of their eventual silence. The active life of a magnetar represents a mere heartbeat in the long chronology of the Milky Way. While a normal star like the Sun will consume hydrogen for 10 billion years, these magnetic monsters burn through their reserves in 10,000 years. The rapid exhaustion of energy occurs because the power source is the decay of the internal magnetic field. In the 1990s, astrophysicists Chris Thompson and Robert Duncan published a series of foundational papers describing the internal thermodynamics of these objects. These researchers argued that the internal magnetic field functions as a dynamic reservoir rather than a static property of the star. The reservoir is subject to the relentless laws of entropy. As the magnetic field lines twist and snap, the energy escapes as X-rays and gamma radiation. The process is inherently unsustainable. The magnetar is essentially a star too bright to survive. By the time the star reaches the age of a human civilization, the magnetic fire has already begun to dim. The transition from a violent broadcaster to a cold remnant is inevitable. The short lifespan means that for every active magnetar we detect, thousands of silent ghosts likely drift through the dark sectors of our galaxy. The mechanics of this cooling involve two primary physical processes known as Hall drift and ohmic dissipation. Within the solid crust of the neutron star, a lattice of ions provides a framework for the most intense magnetic fields in the universe. Electrons move through this lattice, carrying the magnetic field lines. This motion is called Hall drift. As the field lines are pushed through the dense matter of the crust, the lines become tangled and compressed. The tension creates heat. Simultaneously, the electrical resistance of the crust causes the magnetic energy to convert into thermal energy through ohmic dissipation. The conversion mimics how the filament in an old light bulb glows when electricity passes through the metal. The scale represents the primary difference. In a magnetar, the electrical currents are measured in quadrillions of amperes. The immense flow of energy heats the crust to millions of degrees, causing the surface to glow with X-ray light. As the magnetic field decays, the currents weaken. the Hall drift slows down, the ohmic heating fades. The star eventually loses the ability to power the outbursts that once defined the existence of the star. The magnetic field of the star does not disappear, but the intensity drops below the threshold required to shatter the crust. Imagine a massive, heavy iron spring coiled so tightly that the metal is on the verge of snapping. To hold the spring in place, you must exert a force that defies common sense. The potential energy stored in the metal is terrifying. If the spring were to release all at once, the energy would destroy anything nearby. Now, imagine the spring has a tiny, microscopic crack. Every few seconds, a small flake of metal breaks off, and the spring unwinds by a fraction of a millimeter. A small spark of heat is released. Over time, the tension in the metal decreases. The spring is still coiled, but the energy is no longer enough to cause a catastrophic failure. The spring represents the magnetic field of the magnetar. The microscopic flakes are the bursts of radiation. The final state of the spring, where the metal is still bent but the tension is gone, is the waning magnetar. These objects are fleeting because they are born in a state of impossible tension. The only way to find balance is to bleed that energy into the void. The universe does not allow such a concentration of power to persist for long. The hidden nature of this transition was confirmed through the study of SGR 0418 plus 5729. When astronomers analyzed the source, the timing data suggested a magnetic field that was surprisingly weak. The surface field was measured at only 6 trillion Gauss. While the field strength is a massive number, for a magnetar, the value is an order of magnitude lower than expected. Some researchers argue that the object proved the existence of low-field magnetars. However, Nanda Rea and colleagues discovered a hidden complexity. While the dipole field, the field extending far into space, was weak, the internal field trapped within the crust was still a quadrillion Gauss. The star is a waning monster. The remnant is an old magnetar that has used up the visible energy but still hides a lethal reservoir beneath the surface. The discovery created a controversy in the scientific community. If a star with a weak external field can still produce magnetar bursts, then we cannot rely on surface measurements to identify dangerous stars. Could the silent remnants be hiding in plain sight? The silent ghosts might not be as silent as they appear. The short lifespan carries a profound existential implication for our search for life. If magnetars are the primary broadcasters of cosmic signals, and if the active phase only lasts for a few thousand years, then we are only seeing a tiny fraction of the total population. For every flash of radiolight we detect from a distant galaxy, millions of dead magnetars must have already fallen silent. The universe is a graveyard of magnetic giants. The evidence reminds us that we are observing the cosmos during a specific moment in time. We are seeing the brief, violent flashes of stars that are burning out. The realization forces us to confront the temporary nature of all extreme phenomena. The power that magnetars represent is a peak, a summit of intensity that matter can only maintain for a moment before descending back into the quiet baseline of the void. The scream of the magnetar is a signal of the mortality of the star. The star is dying from the moment the star is born. We return to the warning from December 2004, the moment that defined our understanding of magnetar power. A giant flare from SGR 1806-20 reached our solar system from 50,000 light-years away. When that surge reached our world, the wave did more than blind our senses. The wave ionized the sky. The flare was a warning delivered from across the galaxy. If that source had been only 10 light-years away, the pulse would have stripped the ozone from our atmosphere, triggering a mass extinction. The terrifying reality is that magnetars do not give a warning. They do not have a predictable cycle. A star that has been silent for 1,000 years can suddenly release enough energy to sterilize a nearby world. We are living in a shooting gallery where the bullets move at the speed of light. The mechanics of this threat involve the interaction between high-energy photons and the molecular structure of an atmosphere. When a wave of gamma radiation hits a planet, the photons possess enough energy to break the bonds of nitrogen and oxygen molecules. The reaction creates nitrogen oxides, chemicals that act as a catalyst to destroy ozone. Ozone is the only shield protecting biological life from the ultraviolet radiation of the sun. Without the shield, the surface of the planet becomes a lethal environment. Furthermore, the volume of energy deposited into the atmosphere would create a massive thermal shock. The air would heat up by hundreds of degrees in seconds, creating global firestorms and atmospheric collapse. The radiation does more than hit the planet. The pulse fundamentally alters the chemistry of the world. This threat makes the study of magnetars is a matter of civilizational security. We need to know where these monsters hide. Imagine the solar system as a delicate soap bubble drifting through a dark warehouse. Inside the bubble, everything is calm and stable. The walls of the bubble are thin, but they protect the interior from the drafts of the room. Now, imagine someone in a far corner fires a high-powered laser. The beam is invisible as the beam crosses the room. No warning precedes the impact. When the beam hits the bubble, the surface instantly evaporates. The interior is exposed to the harsh environment. The soap bubble represents the magnetosphere of the Earth. The laser is the magnetar flare. This analogy helps us understand our true position in the cosmos. We feel safe because our environment has been stable for millions of years, but the stability is a result of the fact that no flare has hit us recently. We are surviving in a window of probability. Is the bubble intact only because the laser has not yet been pointed in our direction? The mystery of the silent population remains the most troubling part of this reality. Astronomers currently know of about 30 magnetars in our galaxy, but models suggest that millions of remnants should exist within the Milky Way. How many of these millions are magnetars in a state of quiescence? We only discover these objects when they flare. A waning magnetar could exist located just a few light years from our solar system, hiding in the darkness. The star would be invisible to current telescopes because the remnant is not emitting X-rays. Scientists call this the silent executioner hypothesis. We are surrounded by dead stars that still possess the potential for a final, catastrophic outburst. Some researchers argue that we should be able to see the thermal heat from these cooling stars. If a magnetar is only a few thousand years old, the surface temperature should still be millions of degrees. However, at a distance of a few light years, this heat would be a faint infrared signal, easily masked by the dust of the Milky Way. We are searching for a needle of heat in a forest of cosmic fire. The void is better at hiding secrets of the void than we are at finding them. We are mapping the active volcanoes of the galaxy while ignoring the ones that are dormant. The existential weight of living in such a violent cosmos forces a shift in our perspective. We have long viewed the universe as a stable clockwork mechanism, but the magnetar proves that the universe is a series of energetic shocks. We exist in the quiet gaps between the screams. The realization reminds us of the meaning of our safety. Survival is not a guaranteed property of the laws of physics. Our existence is a lucky accident of geometry. If the axis of a magnetar flare points just a few degrees in a different direction, a world is saved. If the axis points toward us, a world ends. The reality reminds us of the staggering fragility of everything we have built. We are a conscious species, living on a thin crust of rock surrounded by magnetic monsters. These monsters could erase our history in a millisecond. This fragility is not a reason for despair, but the reality provides a reason for a profound sense of awe. We are the witnesses to a level of power that exceeds our capacity to control or even fully understand. Magnetars represent more than stars. These objects serve as laboratories where the fundamental laws of the universe are tested to the breaking point. Within a quadrillion Gauss field, the vacuum itself takes on a tangible physical quality. The magnetic pressure is so high that the void is no longer empty. Instead, virtual particles fill the vacuum, ripped into existence by the intensity of the field. This threshold represents the edge of reality. If the field were any stronger, the structure of space would break down entirely. The magnetar is the ultimate demonstration of what happens when energy is concentrated into the smallest possible volume. We are looking at the maximum expression of electromagnetism. Beyond this point, only the void remains. We find ourselves again at that frontier where the standard rules of physics simply dissolve into the unknown. In the quadrillion Gauss field, the vacuum polarization we examined earlier becomes more than a theoretical effect. The void becomes a physical reality. This brings us back to that electromagnetic prism we encountered earlier, where the sheer density of the field forces the vacuum itself to act like a solid lens. The vacuum itself becomes birefringent. Light traveling through this space is split into two different paths depending on the polarization of the light. This birefringence is a property usually reserved for solid crystals like calcite. Everything changed in that moment when scientists realized that the empty vacuum could behave like a solid crystal. Seeing this transformation is one of the most jarring discoveries in modern physics. The effect was predicted in the 1930s by Werner Heisenberg and Hans Euler, but the effect was not observed until astronomers used the Very Large Telescope to look at light from a magnetar. The vacuum is not a passive stage. The vacuum is a participant in the story. The intensity of the magnetar makes the invisible visible. Imagine standing on the shore of a perfectly calm and transparent lake. You can see all the way to the bottom. The lake seems as if the water is not there at all because the water is so clear. Now, imagine a massive, invisible hand reaches into the water and begins to stir the lake with incredible speed. Suddenly, the water is no longer transparent. The motion creates bubbles and vortices. The hand represents the magnetic field of the magnetar. The water is the vacuum of space. The turbulence is the polarization of the vacuum. The analogy helps us understand that the vacuum is only empty because the void is at rest. When you apply enough energy, the emptiness reveals the hidden structure of the vacuum. The magnetar is the hand that stirs the cosmic lake. We are witnessing a threshold where the distinction between physical existence and the void is defined by energy alone. The paradox of the observer is that we are the only part of the universe that can appreciate this intensity. The magnetar does not know that the magnetar is the most powerful object in the cosmos. The magnetic field lines do not care that they are splitting the vacuum. These events are indifferent to their own significance. But we are here. We have built the telescopes and the mathematics required to see through the darkness. This creates a strange symmetry. The magnetar represents the peak of physical power, while the human mind represents the peak of conceptual awareness. We are the mirror that the universe uses to look at universal extremes. The realization transforms the dread of the magnetar into a form of intellectual transcendence. We are small and fragile, but we are also the observers of the absolute. We have named the monster and measured the strength of the monster. The evidence brings us to a final reckoning with the nature of existence. The magnetar is a reminder that the universe operates at scales completely alien to our daily experience. We inhabit a world of soft light and gentle gravity, but that world is an anomaly. The true face of the cosmos is one of quadrillion Gauss fields and starquakes that shatter the foundations of matter. By observing these extremes, we are learning the rules of the game at the highest stakes. We are reaching the edge of the horizon where current understanding ends and something new begins. The magnetar is the lighthouse at the end of the world. The only light that illuminates the path through the void is this terrifying radiance. We are standing at the threshold looking into the heart of the most extreme objects in the universe, and we are finally beginning to understand what we are seeing. The journey through the magnetic fire has led us here, to the moment where the power of the star and the awareness of the mind meet at the edge of the absolute. We have spent these hours descending through the layers of a magnetic abyss. On December 27, 2004, the scientific community received a message that humanity was not prepared to translate. This blast of energy arrived from a source 50,000 light-years away, a dead star known as SGR 1806-20. When the pulse hit the atmosphere of the Earth, the wave physically altered the environment of our world. Every astronomical satellite in orbit was momentarily blinded by a wall of gamma radiation. Researchers like Victoria Kaspi and the team of Robert Duncan and Christopher Thompson spent years deciphering this event. The data revealed the flare was a giant outburst from a magnetar, a moment that served as the starting point for our investigation into the limits of physical reality. This journey took us from the control rooms of the Neil Gehrels Swift Observatory to the distant corners of the Milky Way, where these magnetic monsters hide in the silence of the void. The mechanics of this power reside in the catastrophic decay of magnetic energy. Magnetars are young neutron stars, remnants of massive stars that ended their lives in spectacular explosions. Within these remnants, the magnetic field reaches intensities of 1 quadrillion Gauss. To understand this scale, consider that the magnetic field of the Earth is about half a Gauss. A magnetar field is 2 quadrillion times stronger. This intensity is enough to rearrange the atoms in a human body from thousands of miles away. Power is not derived from rotation. Instead, energy comes from internal magnetic field lines as the lines twist and eventually snap. When the tension becomes too great, the crystalline crust of the star begins to buckle. This failure is a starquake. The rupture releases a torrent of energy that propagates through the magnetosphere, creating the giant flares witnessed in 2004. Thomson and Duncan proposed this model in the 1990s, suggesting the magnetic field acts as a reservoir of energy that must eventually dissipate. Decay is inevitable. The magnetar is a star born with a lethal inheritance, destined to burn out in a short, violent burst of cosmic brilliance. Our investigation then expanded beyond the borders of our own galaxy. We looked at the mystery of fast radio bursts, millisecond-long flashes of radio light arriving from billions of light years away. For years, the origin of these signals was a primary controversy. Scientists debated whether the signals came from black holes or colliding stars. In April 2020, a detection provided the smoking gun. A magnetar within our own galaxy, SGR 1935 plus 2154, released a burst of radio light that matched the characteristics of the distant signals. This connection proved that magnetars are more than local anomalies. Magnetars represent the cosmic broadcasters of the universe. Signals detected from the deep void are the echoes of starquakes happening in galaxies we can barely see. This recap brings us to a humbling realization. We are living in a cosmos that is much more active and dangerous than the ancestors of humanity ever imagined. The sky is not a static ceiling. The sky is a dynamic field of energetic thresholds. We have traced the life of the magnetar from the birth of the star to the cooling of the field. We have seen how these objects define the boundary of what matter can survive. This journey was a descent into the heart of power. We have looked into the abyss, and the abyss has looked back at us through the lens of a quadrillion Gauss field. The evidence is complete. The story of the magnetar is the story of the maximum expression of electromagnetism in the universe. We are now ready to consider what this peak of power means for the ultimate destiny of the cosmos. The primary finding of our investigation is that the universe operates at intensities that challenge the limits of human imagination. We often think of space as a vacuum, a cold and empty place where nothing happens. The magnetar proves that space is a medium that can be polarized, warped, and broken. When a magnetic field reaches 1 quadrillion Gauss, the vacuum itself becomes birefringent. This means the void acts like a crystal, spitting light into different paths. This level of intensity represents a point where the distinction between matter and energy begins to dissolve. We have measured the temperature of the magnetar crust at millions of degrees. We have seen magnetic pressure so high that the pressure could compress an entire planet into the size of a marble. These numbers are more than statistics. These measurements represent the absolute peaks of physical reality. The magnetar is the laboratory of the universe. a place where the laws of physics are pushed into regimes that do not exist anywhere else. This realization forces us to acknowledge that our daily experience is a rare and sheltered exception to the rule of cosmic violence. Within the magnetosphere of a magnetar, the physics of the void undergoes a radical transformation through vacuum polarization. In a standard environment, the vacuum is considered empty, a background stage where particles interact. However, quantum electrodynamics predicts the vacuum is filled with virtual particles, pairs of electrons and positrons that spontaneously appear and disappear. Normally, these particles are invisible because they exist for such a short time. But the magnetic field of a magnetar is so intense that the field can rip these virtual pairs apart before they can annihilate. The vacuum becomes a physical, polarized substance. This intensity creates a state where magnetic energy density exceeds the mass energy density of the matter itself. The field is more substantial than the star. This is the threshold of vacuum breakdown. Heisenberg and Euler predicted this effect in the 1930s, but the magnetar is the only place in the cosmos where the effect can be observed. Findings show the universe has a hidden texture. The void has a breaking point. When you apply enough magnetic pressure, the emptiness reveals the underlying structure of the quantum world. The complexity of these findings is increased by the discovery of low-field magnetars like SGR 0418 plus 5729. As Nanda Rea demonstrated, a star can appear weak on the surface while hiding a lethal intensity within the crust. This means our current map of the magnetic universe is likely missing the majority of the population. We are only seeing the monsters currently screaming. These findings suggest the universe is far more crowded with extreme objects than we previously suspected. Research indicates the magnetar phase might be a universal stage of stellar evolution for all massive stars. If the universal stage theory is true, then the galaxy is filled with silent reservoirs of magnetic energy waiting for a final starquake to announce the presence of the stars. Findings challenge the idea that we can categorize stars by surface appearance. The true nature of the star is hidden in the depths of the crust. The anomaly of the low-field magnetar is a warning that the cosmos hides the most dangerous secrets in the dark. These findings lead us to a profound conclusion about the nature of the laws of physics. We are more than observing a star, we are witnessing a limit. The magnetar represents the maximum concentration of energy that the universe allows before the structure of space itself must change. This intensity is a fundamental constant of our reality. The existence of magnetars proves the universe is capable of generating conditions that would erase the existence of humanity in a heartbeat. But the existence also proves the universe is governed by laws that remain consistent even at the edge of the absolute. We are looking at the foundational architecture of the cosmos. These findings are a reminder. The universe is not designed for the comfort of humanity. The universe is designed for the expression of power. We are the witnesses to that expression, and our understanding of these intensities is the measure of our growth as a conscious species. The paradox of the magnetar is that the star is simultaneously the most destructive object in the cosmos and a primary tool for universal communication. A giant flare from a magnetar possesses the power to strip the atmosphere from a planet across the void. If a flare hit the Earth from a distance of 10 light-years, the radiation would trigger a mass extinction. This magnetar is a silent executioner, a monster that could end the story of humanity without warning. Yet, these same violent outbursts are the source of fast radio bursts, signals that travel billions of light-years to reach our telescopes. The magnetar is a lighthouse in the dark that allows us to map the structure of the distant universe. This is the dual nature of the extreme. The same energy that destroys also illuminates. The star representing a lethal threat to life is also the star providing the data we need to understand the history of the cosmos. The paradox forces us to view these objects as both a danger and a gift. The mechanics of this communication involve the propagation of radio waves through the intergalactic medium. When a magnetar starquake occurs, the rupture creates a shockwave that travels through magnetic field lines. This pulse becomes smeared, a phenomenon called dispersion. By measuring the amount of dispersion in a fast radio burst, astronomers can calculate the amount of matter the pulse encountered on the journey. Instead of just a star, the magnetar is essentially sending us a report on the contents of the intergalactic void. We are using these flashes of radio light to weigh the universe. Data from these bursts has allowed scientists to find missing baryonic matter that was previously invisible. The paradox is that the most violent events in the universe are the events providing the most precise measurements of the cosmos. Destruction of the magnetar crust is the mechanism that allows us to read the history of space. Imagine a person standing on a dark mountain at night holding a massive crate of fireworks. If the person sets off the fireworks all at once, the explosion is terrifying. Anyone standing nearby would be blinded by the blast. However, for a traveler lost in the valley miles away, the flash is a lifesaver. This traveler uses the light to see the path and determine how far away the mountain is. The explosion is a danger to the person on the mountain, but the explosion is a signal for the traveler. The magnetar is the person with the fireworks. We are the travelers in the valley. We need the violence of the explosion to see the path through the darkness of the void. Light that could kill us if we were too close is the light that guides us when we are far away. Complexity of this paradox is increased by the rarity of the active magnetar phase. Because a magnetar only burns for 10,000 years, we only see a tiny fraction of the total population. Signals we receive from distant galaxies are incredibly precious. Each fast radio burst is a unique message from a star already dying. Instead of typical pulses, we rely on the brief screams of these dying giants to understand the structure of the cosmos. If magnetars lived longer, the sky would be filled with radio light and signals would overlap into a chaotic noise. Brevity of the magnetar life is what makes communication possible. Mortality of the star is a requirement for clarity of the signal. The paradox reveals that the universe uses the death of matter to create signals of discovery. The paradox of the magnetar brings us to a fundamental question about the relationship between life and the cosmos. Are we surviving because the universe is a safe place, or are we surviving because we have learned to read the warnings of the monsters? The magnetar is a reminder that the environment of humanity is a fragile bubble in a violent sea. We have used radio light from these stars to expand our awareness, but the light also reveals how easily we could be erased. This is the existential tension of the modern era. As conscious observers, we occupy a unique position as the only entities capable of comprehending the profound irony of these celestial monsters. We have turned a lethal threat into a scientific tool. The paradox of the magnetar is the paradox of humanity. Our physical existence remains insignificant in the face of such power, yet our intellect allows us to harness the radiance of the absolute and transform that energy into deep, scientific understanding. Destruction of the star is the birth of our understanding. We have reached the end of our journey through the magnetic fire. We have seen the blinding light of the 2004 flare and the silent decay of the internal magnetic field. We have examined mechanics of vacuum polarization and the unified theory of fast radio bursts. Evidence is clear. Magnetars are the peak of electromagnetic power, the extreme limit of what matter can achieve before descending into the silence of the void. These objects are the sirens of the cosmos, signaling the boundaries of the physical world. Every star, every field, and every galaxy is subject to the laws of entropy. The magnetic fire must eventually fade. This looks like a story of inevitable collapse. From the perspective of the universe, the magnetar is not a disaster. The magnetar is an opportunity. Existence of such intense power proves that the universe is capable of creating complexity out of chaos. The fact we can observe these objects, name these objects, and measure the fields of these objects is the most significant event in the history of the star. The magnetar represents the maximum expression of physical energy, but the human mind represents the maximum expression of awareness. We have crossed a threshold where the universe is no longer just a collection of violent events. The universe has become conscious of itself. We are the observers who give the giant flare the meaning of the event. Without us, the magnetar would scream into the void, and no one would hear the message. With us, the scream becomes a data point. Violence becomes a law of physics. Destruction becomes a story. This is the optimistic pivot. We are far from victims of cosmic forces. We represent the consciousness that transforms those forces into understanding. The realization of this consciousness changes the meaning of our insignificance. Yes, we are small compared to a quadrillion Gauss field. Yes, we are fragile compared to a starquake. But the field cannot understand the field. The star cannot observe the star. We are the part of the cosmos that has developed the ability to look back at origins of the cosmos and ask why. The magnetar represents far from a graveyard of dead matter. The universe represents a system that creates observers. Fate of matter involves more than cooling and fading. The fate of matter involves becoming aware. We are the climax of the story of the star. Energy that burns in the heart of the magnetar is the same energy that allows us to think and to wonder. We are made of the same material as the monster, but we have turned that material into thought. The choice is ours. We can choose to look at the magnetar and feel despair at the scale of our vulnerability, or we can choose to look at the magnetar and feel awe at the scale of our achievement. We have mapped the most extreme objects in existence. We have deciphered signals of the void. This awareness is the most powerful force in the universe. We are at the edge of a new era of understanding. The question is not whether the magnetar will destroy us. The question is whether we will continue to grow until we are capable of surviving the realization of our place in the cosmos. The universe does not just create stars. The universe tests the limits of existence. And we are the answer to that test. Everything changed in that moment when we realized that we are far from simply looking at the universe. We represent the universe looking at itself. The magnetar is the final proof.